Ever wonder how Google and Apple autocomplete searches so quickly? Implement Trie, Prefix Tree, is a Pattern Mastery 100 staple, and a favorite at top tech interviews for testing your ability to design efficient string data structures. Over 30% of candidates struggle to code correct insert, search, and prefix logic under pressure. Master the Trie, and you'll ace not just interviews, but also real-world search systems. Let's break down Implement Trie, Prefix Tree, with the basic framework, a powerful way to design and implement complex structures in interviews. You're asked to build a data structure that supports three operations. Insert, word, adds a word to the trie. Search, word, returns true if the word is in the trie. Starts with prefix, returns true if there's any word in the trie that starts with the given prefix, input/output. Insert and query words/prefixes, all lowercase English letters. Trie supports OL time per operation, where L is the length of the word/prefix. Picture a search engine's autocomplete, or a phone book lookup that instantly finds all contacts by prefix. Interviewers might ask, how would you optimize prefix queries in a massive dictionary or suggest words in a typing app? What's tricky? You need efficient insert/search/prefix checks, all in OL time. The structure must handle a dynamic set of words with overlapping prefixes. Avoid confusion between a node being a prefix and being the end of a valid word. Think step by step. Represent the trie as a tree where each node is a letter, and paths from the root to nodes spell words/prefixes. Each node contains a mapping from characters to child nodes, usually a fixed size array for 26 letters, or a hash map. A Boolean flag indicating if a word ends at this node is _end. For insert, word, start at the root for each character, create or move to the child node. After the last character, mark is _end true. For search, word, walk down the tree per character. After the last, return true if is _end is set. For starts with, prefix, same as search, but return true as long as you reach the last prefix character. Let's clarify. Insert and search both use the same traversal logic. Only difference, search checks is _end. Starts with doesn't. Trie saves huge space on repeated prefixes compared to storing all possible words. Edge cases. Empty string insert/search, prefixes that are full words versus partial prefixes. Define a trie node class. Children, mapping for 26 letters, array or dictionary is _end, Boolean for word end. Trie class. Root node, empty methods. Insert, search, starts with. For each operation, loop character by character, branching through the tree. Now let's implement the dictionary-based trie, storing each node's children in a hash map for flexible and clean prefix operations. We start by defining a trie node. Each node represents one character in a word. In the nodes constructor, we set up two things. Children, a dictionary mapping letters to the next trie node. Is_end, a flag marking whether this node ends a complete word. This dictionary will store all child characters branching from this node. It grows dynamically as we insert more words. Initially, the node does not represent the end of a word. We flip this later when a word finishes here. Next, we define the main trie class, the structure that manages the whole tree. The trie starts with a single root node. It doesn't store any character, it's simply the starting point. We initialize that root node right here. Let's define how to insert a new word into the trie. This operation runs in OM time, one step per character. We begin at the root. We'll walk down the trie character by character. We loop through each character of the word we want to insert. If the current character does not exist as a child, we need to create a new path for it. We create a brand new trie node for this new character branch. We then move into that child node, walking down the trie like following a trail of breadcrumbs. When we finish processing every character, we mark the final node as the end of a valid word. This function checks if a full word exists in the trie. Again, time complexity. OM. We start at the root. We walk through each character of the target word. If any character is missing in the trie, the word cannot exist, so we return false. If the character exists, we follow it to the next node. After processing all characters, we return whether the final node marks the end of a word, which ensures we're not mistaking prefixes for whole words. This function checks if any word in the trie begins with the given prefix. Just like before, we start at the root. We scan each character of the prefix. If a character is missing, no word in the trie can start with this prefix. So we return false. Otherwise, we follow the path deeper into the trie. If we make it through every character, then yes, the prefix exists in the trie. And that's how this algorithm works. It first uses a dynamic dictionary-based node system to build flexible word paths, then lets us search full words or prefixes in linear time. Efficient, simple, and elegant. Let's check. These operations describe how we interact with our trie. Try create a new empty trie. Insert Apple search app starts with app insert app search app, again. With the Dictionary of Children implementation, each node stores a map like char, child node, and a flag is end to mark the end of a word. Let's walk through the sequence. Trie just initializes the data structure returns null. Insert Apple we create nodes for apple if they don't exist and mark the last node as end of word. Return null. Search Apple. We traverse character by character. A, P, P, L, E. We land on the node for E and it's marked as a complete word return true. Search app we follow app. That node exists, it's a prefix, but we haven't marked app as a full word yet return false. Starts with app same traversal as above, app. We only need the prefix to exist, not the full word return true. Insert app. We go to the existing node for app and now mark it as a complete word. Return null. Search app follow app again. This time, the app node is marked as end of word return true. So our result list becomes null, null, true, false, true, null, true. And that's exactly what our implementation produces. Every operation's result lines up with the expected behavior. So, our implementation is correct. The dictionary-based trie handles inserts, exact searches, and prefix checks in OM time per operation and passes this test case perfectly. Now let's implement the array-based trie, using a fixed 26-slot structure at every node for fast, index-driven character access. We start by defining a trie node. Each node represents a single character but, unlike solution 1, this node has exactly 26 slots, one for each lowercase letter. Here we create a fixed size array of 26 elements. Each position corresponds to a letter. Index 0 for A, 1 for B, all the way to 25 for Z. This makes accessing a child node extremely fast, constant time, 01. We mark whether this node represents the end of a valid word. At creation, it does not. Now we define the main trie structure that uses these nodes. Every trie starts with a root node. It doesn't store a letter, it's simply the entry point. This method inserts a word character by character into the trie. Because we handle each character once, the time complexity is OM. We begin at the root and will walk downward as we process each letter. We loop through each character of the input word. Here's the key difference with solution 2. We convert the character into a number between 0 and 25 by subtracting A from that character's ASCII code. This gives us the correct slot in the children array. If there's no child node for this character yet, we create one, building the trie branch as needed. We initialize a brand new node at that index. We then move down into that node and continue adding letters. When we finish processing the final character, we mark the node as the end of a complete word. This method checks whether a full word exists in the trie. Again, time complexity, OM. We begin from the root. We inspect each character of the word. We convert the letter into an array index. If the needed branch is missing, then the word cannot exist, return false. Otherwise, we move deeper into the trie. At the end of the word, we return whether this node actually marks a valid word end. This function checks if any stored word begins with the given prefix. Also runs in OM. Start at the root. Loop through each character of the prefix. Convert the character into the appropriate index. If a character path is missing, this prefix doesn't exist in the trie, return false. Otherwise, keep following the prefix downward. If we survive the entire prefix, that means at least one word starts with it. And that's how this algorithm works. It first sets up a fast, fixed-size array of child nodes, then uses that structure to insert, search, and check prefixes in linear time. Efficient, simple, and elegant. Let's check. We'll run the exact same sequence of operations, but this time using a trie where each node has a fixed array of 26 children, one slot per lowercase letter AZ. In this version, instead of a dictionary, each node holds an array like children 26 and an is-end flag. The character C maps to index C, A. Walking through the operations. Trie creates an empty root node with all children set to null returns null. Insert Apple for each character. A index 0. P index 15. P index 15. L index 11. E index 4. We create nodes along this path and mark the E node as is-end equals true. Return null. Search Apple follow the same indexes for Apple. We reach the E node and see is-end equals true return true. Search app traverse indices for a, P, P. The node for app exists, but is-end is still false at this moment return false. Starts with app again traverse app. We only need the path to exist, not is-end return true. Insert app. We go back down to the app node and set is-end equals true. Return null. Search app traverse app once more. Now is end is true at this node, return true. So the final output is null, null, true, false, true, null, true. And that's exactly what we see from the program. The output matches the expected result step by step. So, our implementation is correct. The fixed array trie mirrors the behavior of the dictionary-based trie, still running each operation in OM time, and it cleanly passes this test case too. Autocomplete isn't magic, it's structure. Implement trie, prefix tree, turns fast prefix lookups into a simple, repeatable pattern. Nail this, and you're designing the backbone of search suggestions and instant lookups. Let's do a recap. We built a data structure that supports 3 core operations. Insert a word, check if a full word exists, and check if any word starts with a given prefix. Each operation works in OL time, where L is the length of the input word or prefix. The main challenges were keeping operations efficient, sharing overlapping prefixes to save space, and clearly distinguishing between this path exists and this path is a complete word. That last point, marking word ends, is where many implementations go wrong. Conceptually, the trie is a rooted tree where each edge represents a character. Every node stores a set of outgoing character links to children, a Boolean flag indicating whether a complete word ends at that node. Insert, search, and starts with all walk the same path character by character. The only difference is whether we require that end of word flag at the finish. We followed that plan precisely, traversed from the root, created nodes as needed on insert, checked for missing links during queries, and relied on the end of word flag to distinguish full matches from mere prefixes. We ran the solution on LeetCode, no errors. Our tests confirmed the behavior. After inserting apple, a full word search for apple returned true, app returned false until we inserted it, and starts with app, correctly returned true the whole time. Edge cases like empty strings and missing prefixes behaved as expected and passed the LeetCode checks. The big takeaway: the trie turns repeated work into shared structure. By separating path exists from word ends here, you get fast, reliable prefix queries, exactly what high-performance search features need.